Okay, so imagine for a second that you're picking up a book. It's written in a language you learned years ago, but haven't practiced much. Let's say it's German or French.
Right. You know the words, but...
Yeah, exactly. You look at a sentence. You recognize every single word. You know cat, you know mat, you know sat. But because you've forgotten the grammar or the structure, you have no idea what is actually happening.
You know the vocabulary, but you don't know the story.
Exactly. Did the cat sit on the mat? Did the mat sit on the cat? Or is the cat just named Matt? You have all the pieces, but without that blueprint, it's just noise.
That is a perfect, if slightly terrifying analogy for where we are today. You have the raw data, but without the structure, you have zero meaning.
And that is exactly where we find ourselves in our journey through compiler design. Welcome back to the deep dive.
Today, we are moving up a level. We are leaving the world of the scanner, which was all about identifying those individual words, and entering the domain of the parser. This is the moment where meaning begins to emerge. We're getting into the Class 10 notes on syntax analysis and Chapter 4 of Thane's book. The mission today is to understand how a compiler takes that flat stream of tokens, that list of cat, sat, mat, and builds a hierarchy of meaning without getting hopelessly confused.
A hierarchy of meaning. I like that. It sounds almost philosophical. But before we get too deep, let's ground this. We have a pop quiz, I see.
And we do. And this is crucial because if you don't understand the input, you can't build the output. So thinking back to our last deep dives, the lexical analyzer or the scanner, what specifically did it give us?
It gave us tokens. It chewed up the raw source code, all the characters, and spat out a stream. ID plus ID semicolon. But crucially, it's just a flat list. It's like a tape.
Precisely. And that tape is the input for today. The parser takes those tokens and produces something far more complex. It gives us a parse tree or, eventually an extract syntax tree.
Okay, let's visualize this. I'm looking at the slides here, and there's this diagram of a tree. But of course, being computer science, it's upside down. The root's at the top.
In computer science, trees almost always grow downward. It's just one of our quirks. But the anatomy is what matters. At the very bottom, the leaves of the tree. That's your actual code. That's the tokens. A plus A, B.
And the branches, the parts in the middle.
Those are the internal nodes, the joints where branches come together. Those are your grammatical categories, things like expression or STMT for a statement. And at the very top, the root is the start symbol. Usually that represents the entire program.
This is the aha moment for me. When we write code, we type it line by line. It feels so linear, top to bottom. But the computer doesn't see a line. It sees a geometry.
That is the key insight. The shape of the tree defines the meaning of the code. If the tree branches one way, your program does one thing. If it branches another way, it does something else completely. And the set of rules that tells us how to grow that tree, that's called a context-free grammar, or CFG.
A CFG. Okay. Context-free implies something specific, right? It means the rules don't care about what's around them.
Exactly. It's a modular system. If you have a rule for an expression, you can swap in that rule anywhere and expression fits. It doesn't matter if it's inside an if statement, a while loop, or a function. The rule for expression is always the same.
And the notation we see in the notes, like $1 to XYY, that's just a substitution rule.
It is. It just means A can be replaced by X, then Y. Simple as that.
And the superpower here, I'm guessing, is recursion.
It is. A rule can refer to itself. You can have an expression that contains another expression, which contains another expression, and so on. That's how we get this infinite complexity programs with millions of lines from a grammar that might only be a few pages long.
But here's where it gets really interesting, and honestly, a little dangerous. Because sometimes the rules aren't as clear as we think. We enter the realm of the villain of our story, ambiguity.
Ambiguity is the absolute enemy of the compiler. As humans, we deal with it all the time. If I say, I saw the man with the telescope, you kind of figure it out from context. Did I have the telescope or did he? But a compiler cannot guess.
The slides have a great example of this using basic math. We have the statement A equals B plus CA.
Right. Now, we all learned PEMDAS in school. We know multiplication comes before addition, but a raw grammar doesn't know that. It just knows tokens.
So if the grammar is ambiguous, you could technically draw two different trees for that one single equation.
Exactly. Visualize it. You could draw one tree where the B plus C is grouped together first in a little subtree at the bottom.
Which means the computer would add B and C and then multiply the result by A.
Which is just wrong math.
And the other tree.
The other tree groups CA at the bottom, so that happens first. Then you add B to that result, and that's the correct math. If your grammar allows both trees to exist, your compiler is essentially flipping a coin to decide how math works.
That is terrifying. But math is one thing. The notes mention something called the dangling else. That sounds like a cliffhanger in a bad soap opera.
It's a logic nightmare. Imagine you have a nested statement. If done, if denom equals 0 or else.
Okay, I see it. You have two ifs and only one else. So who does the else belong to?
Does it belong to the first if, meaning if not done, do the else? Or does it belong to the second if, meaning if done but denom is not 0, do the else?
And just like the math example, if the grammar is ambiguous, the compiler has no idea. It could attach that else to the outer if or the inner one.
And this isn't just theoretical. This fundamentally changes the flow of your software. If you write code expecting one behavior and the compiler parses it the other way, you have a bug that is nearly impossible to find because the code looks perfectly fine.
So how do we fix it? Do we just rely on indentation like Python does?
In this context, we fix it in the grammar itself. The slides show a solution called the matched versus unmatched grammar.
I looked at that slide. It looked incredibly dense. It was like a team T matched, unmatched. It felt like we were just adding more words to hide the problem.
It looks dense, but the logic is actually pretty elegant. We force the grammar to distinguish between a statement that has a closed else, which we call matched, and one that doesn't, which is unmatched. Essentially, we rig the rules so that an unmatched statement can't sit in a position where it would steal an else.
So you're literally making the ambiguous tree impossible to even build.
Yes. We bake the logic into the shape of the tree rules. We force the else to bind to the nearest open if.
So we are essentially restricting the freedom of the tree so it can only grow in the correct shape.
Precisely. Structure is constraints. And that brings us right back to that math example. We don't tell the compiler, multiply first by setting some flag. We structure the grammar so that multiplication has to happen deeper in the tree.
This is the concept of precedence. I want to drill into this because it feels like the key takeaway. It's like depth equals priority.
That is the perfect summary. In a parse tree, operations that happen at the bottom in the subtrees are resolved first. Their results are passed up to the nodes above them.
So to make CA happen before B+, we have to shove the multiplication logic lower down in the tree's hierarchy.
Correct. That's why you see grammars split into layers. You don't just have one big rule for expressions. You have factors and terms and then expressions.
Right, I saw that. A factor is usually just a number or an ID. A term is factors multiplied together, and an expression is terms added together.
Exactly. And because an expression is defined as a sum of terms, the term, which handles multiplication, is a child node. It is lower. It must be resolved before the expression itself can complete.
So you're building PEMDAS into the architecture of the tree. You aren't writing a rule that says multiplication is greater than addition. You're building a geometry where addition literally sits on top of multiplication.
You are building the rules of the universe into the structure of the language itself.
That is wild. Okay, so we have our tree. We know how to handle ambiguity by layering our grammar, but now we have to actually build this thing. The slides talk about syntax, parsing, complexity, and there are some scary big O notation numbers here.
There is a tension here between theory and reality. If you want a parser that can handle any grammar you can dream up, what's called generalized parsing, it takes $3 time.
Let's put that in perspective. If I have a program with, say, 1,000 lines of code, $3 is a, what, $1 billion operations?
Roughly, yeah. Now imagine compiling a browser or an operating system with millions of lines of code. If it took $1 time, you'd hit compile and come back next year. It's functionally impossible.
So we cheat. Or compromise.
We compromise. We don't use generalized grammars. We design programming languages to use restricted grammars, specifically ones called LL or LR. And these allow us to parse in otter time, linear time.
Linear speed is essential. You want the compile time to grow proportionally to the code, not exponentially. But what are we giving up? Why is an LL grammar faster?
We are giving up ambiguity and backtracking. In a generalized parser, the computer might try to build a tree branch, realize halfway down it doesn't work, back up, destroy the branch, and then try another one. That's incredibly slow.
It's trial and error.
Exactly. In our restricted LL grammar, which is what the students will be using, we use what's called predictive parsing. We want to look at a token and know instantly which rule to use. No guessing.
And the most common way to implement this is something called recursive descent.
Yes. Imagine the parser is standing at the root of the tree. It looks at the very first token and asks, okay, which rule applies here?
It's like a choose-your-own-adventure book.
It is. I see an IF token, therefore I will call the parseSafe function. That function then might look for a condition, then call it this parse statement. It walks down the tree as it builds it.
But wait, what if it's not obvious? What if I see an ID token? That could be the start of an assignment like x5, or it could be a function call like x. How does the parser know which path to take without guessing?
That is where look-ahead comes in. The parser is allowed to peek at the next token, or maybe the next few tokens, to decide which path to take. It's like looking through the keyhole before you open the door.
So, I see an ID. I don't know what to do yet. Let me peek at the next token. Oh, it's an equal sign. Therefore, this must be an assignment.
Exactly. And because we restricted the grammar, that LL stuff we mentioned, we can guarantee that peeking just one token ahead is usually enough to make the right decision without any doubt.
So we design the language itself so that the signs are always visible. We force the programmer to write unambiguous code so the parser never has to guess.
Exactly.
So we've moved from the chaos of raw tokens to the beautiful order of a parse tree. We've defeated the ambiguity villain, and we've done it in linear time. But now, you have to pause the simulation and look at the calendar on the wall.
We do. Time waits for no compiler.
Today is Saturday, February 14th, 2026. Happy Valentine's Day to all our listeners who love syntax trees.
Nothing says romance like a well-formed abstract syntax tree. Maybe a bouquet of tokens.
I think I'd prefer chocolates. But looking ahead, we have a bit of a timeline disconnect here. We've been talking about parsing today. That's the topic of the lecture. But the immediate deadline for you, the listener, is actually the step before this.
Right. Lab 3, the B minor scanner, is due on Monday, February 23rd.
So do not start writing your parser yet if you haven't finished your scanner. You can't build a tree if you don't have the leaves.
And remember, the scanner needs to be robust. It needs to handle comments, strings, all the weird characters. If your scanner is broken, your parser doesn't stand a chance. You'll be debugging the parser thinking your logic is wrong, when actually your scanner is just feeding it garbage tokens.
That is a special kind of hell. Avoid that. Finish the scanner first. Also coming up on the horizon, Wednesday, February 18th, we're looking at Appendix B of the compiler's book.
That appendix is the constitution of the B minor language. It describes the specific grammar you will be implementing. It's not just reading, it's your instruction manual. You need to read it with a fine-toothed comb to understand the precedence rules we just talked about.
Then Friday, February 20th, is the LLM Roundtable. The topic is Jan LeCun has been right.
That should be a spirited debate. LeCun has some very strong opinions on the nature of intelligence. He argues that current LLMs are just predicting the next token, which is very similar to our parser, but they lack a world model.
Which ties interestingly into our discussion today. Our parser has a world model. It's the context-free grammar. It knows what is legal and what isn't, and LLM just knows probabilities.
Exactly. It's the difference between true structural understanding and really, really good mimicry.
And don't forget the Sunday routine, February 22nd, journal entry. The 2-1 rule still applies.
2 paragraphs, 1 quiz question. Keep that reflection habit going. It really helps solidify what you've learned.
So what does this all mean? We've unpacked a lot today.
If there's one thing to take away, it's this. Structure is meaning. We tend to think of code as a list of instructions, like a recipe, do this, then do that. But to the machine, code is a geometry. It's a tree.
It changes how you look at your IDE, doesn't it? You're not writing lines, you're growing branches.
You are. And if you aren't careful with your grammar, if you leave those dangling else's or ambiguous math operations, you are growing a twisted tree. The leaves might look right, but the fruit, the execution, will be poison.
That is a dark but effective image to leave on. So watch your dangling else's, keep your precedents straight, and get that scanner finished so you can start planting your trees.
And good luck with Lab 3.
Thanks for diving in with us. We'll catch you next time.